Myself Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering. So in the today's lecture, we are going to learn the two topics which are associated in the electric fields in material media called convection and conduction currents, along with that continuity equation. Right? So here, this first topic we are going to learn here is a convection and conduction currents, then followed by continuity equation. So before going to learn what about convection current and conduction currents, then continuity equation, then how the materials are broadly classified according to that, how many types of materials are there, then what are the properties, then we'll go for respective currents. So here conduction, in order to define this conduction and convection currents, then along with that currents we are going to also learn as densities of the respective currents as conduction current density and convection current density. Now before going to learn about this convection and conduction currents, let us see the classification of the materials. How these materials are classified first of all means basic electrical materials may be classified in terms of their electrical properties like conductivity, which is denoted with the notation called sigma, as conductors and non-conductors, or technically these conductors and non-conductors respectively are called as metals or and insulators. These insulators are also called as dielectric materials. So in our complete discussion related to electromagnetic waves and transmission lines, we have considered instead of insulators, we are going to use the term called dielectric materials. Right? So basically, the fundamental electrical property of the materials as conductivity, depending upon the conductivity, materials are broadly classified into conductors and non-conductors, and these are technically termed as metals and insulators, whereas insulating materials are also called as dielectric materials. Now, what do you mean by conductor and what do you mean by insulating material? So, if the conductivity lies between these two, what is that material called? Means, first of all, a material with high conductivity means if sigma is denoted with the conductivity, then the condition is to be considered for the metal or conductor is here. Sigma is far greater than that of 1. Means ideal value of the conductor is equal to infinite. Right? So, a material with high conductivity, the condition here we have considered is sigma is far greater than that of 1 case, a material is said to be metal or conductor. And here are the some of the examples for the metals or conductors for copper and aluminium, which gives us highest conductivity. Now, a material with low conductivity means the condition which we have considered for that insulating material is sigma is far lesser than that of 1 is termed as an insulator. Now, examples of this material which is insulating material is glass, rubber, wood, etc. Now, the conductivity which is lies between the metals and the insulating materials are called as semiconductors. So, generally used semiconductors are here silicon and germanium. And along with this, three types of the materials, like first one is conductors, and the second is insulators, also called as dielectric material. Now, third one is here semiconductor. So, along with this three types of the materials, we are also having superconductors. So, what do you mean by superconductor? So, as we know that the definition for conductor means ideal value of the conductor should be sigma equal to infinity, and for insulators that sigma value is equal to 0, and for the semiconductors that sigma value which is lies between metals and the insulators. Now, along with this three types of the materials, we also have the fourth type of material called superconductor. So, what do you mean by superconductor? Means at absolute temperatures it exhibits, means at absolute temperatures means 0 T equal to 0 degree Kelvin, then some of the materials which exhibits infinite conductivity. conductivity. So these are the materials which are said to be superconductors. Then examples are lead, aluminum are the best examples for superconductors. Now depending upon the fundamental electrical property of the materials called conductivity, materials may be broadly classified into three types: conductors, insulators, also called as dielectric materials, and third one called as semiconductors. Then we have seen some of the examples of respective as for the metals as copper and aluminum, for the insulators as glass and rubber, and for semiconductors silicon and germanium. Now depending upon this one, we are going to learn the first term called here as convection current. As the name itself tells us that convection doesn't require any conducting medium to generate such current. So, without considering any conducting medium, how the current is generated means by considering a simple example, we'll analyze what do you mean by convection current. Now, from this convection current, we are going to derive the equation for its density as denoted with as Jc. So, J is the notation for current density and C stands for here convection current, right? In the previous lecture, we have discussed energy density. So, energy density means energy per unit area. So, similarly, here also current density can be defined as current per unit area. So, in order to define this current density, first of all, what do you mean by current? How it is to be generated? Now, with the example, how the convection current density is to be derived. Now, first one, general definition of a current means I, the flow of electrons is said to be a current, or in terms of mathematical equation, we can say that the current I can be denoted or defined as charge per unit time, and it is given by here I equal to dq by dt. So d is the notation for differentiation, means for small currents we are representing it with differentiation notation as d. Hence I equal to dq by dt. So consider this as equation number 1. Now statement is given by here the current through a given area is the electric charge passing through the area per unit time. Means charge per unit time we have defined it as current and it is denoted with the mathematical equation as I equal to dq by dt. So in general we can define it as I equal to q by t, means charge per unit time. Then if you consider for the differentiation, the term I equal to dq by dt. Now, if current delta I, where this delta is denoted with, now to represent a small change, we use here this delta. So, if current delta I, a small change in the current, we represented it with delta I, and which is flows through a planar surface. So, here the current is represented with small change, hence the surface area is also denoted with a small change case, hence the notation for that is delta S. Now, for a planar surface area, delta S and the current density is given by, as we know that current density. So, in the previous lecture we have discussed energy density means energy per unit area. Similarly here, current density means current per unit area, I by S. So, for a small change case, we are representing with the current as delta I and the area as delta S. Hence, the current density J is given by delta I by delta S. Now, from that, we are deriving the equation for delta I, and which is equal to J into delta S. Now, consider this that as equation number 2. And previously, we have defined in general current per unit charge per unit area can be defined as the current, hence I equal to dq by dt. Similarly, here the small change in the current's case we are denoted with the notation as delta I, which is equal to J into delta S. So the total current flowing through as a surface area is S. Then I equal to integral S J dot ds. Now here differentiation element means di equal to J into ds. Now if we are going to derive this equation from I, now both sides we are considering integration. Then here differentiation integration gets cancelled. I equal to integral S J dot ds. Why it is S means here we are considering differentiation with respect to the surface. Hence the integration term becomes I equal to integral S J dot ds. So total current which is flowing through a planar surface is given by I equal to integral S J dot ds. Now again consider this as equation number 3. Now to analyze that convection current. So these are the general definitions for, according to the general definition of a current, I equal to dq by dt. If we consider small change in that current, then in terms of current density, it can be given by delta I equal to J into delta S. Now, the total current which is flowing through that planar surface area, hence I equal to integral S J dot ds. Now, according to these three equations, now we are going to derive the equation for convection current density. So to derive that, here we'll consider one simple figure. So this figure represents here current in a filament. Suppose the current which is carrying through a filament we are considering here. So here the cubical object, and each object will have an area of plate area of delta S, and each plate area means each cubical objects which are cutted into equal spaces, then the area which is occupying in this cubical object is denoted with delta S, and the between two planar surface areas the length is given by delta L, and in this throughout this cubical object the charge density is given by rho v. So rho v is nothing but here volume charge density, and here if we consider the directions of this respective one, first one as x, and if we are considering second direction as here y, and let it be this as z. So along this three directions, see here if you observe the thicker line which is denoted with u. So the velocity of an electron which is directed in the which direction? Y direction. Why? Because here we are representing with y direction, and the electron direction is along the y. Hence, velocity of electron is located or directed in y direction. So why we have considered y direction means here, see first, consider a filament of the above figure, this figure. Then if there is a flow of charge of density, so charge of density, and it is denoted with J, charge of density denoted with rho v. So why? Because cubical object we have considered means three directions we have considered. So if you consider three directions, then the charge density is given by rho v. So if you are considering it for volume charge, then we have to consider in three directions as x, y, z directions, then rho v at a velocity. So it is given by u equal to uy into ay. So u is a vector here, and u will be the magnitude of the component in y direction, and ay be the unit vector direction for that respective. So u equal to uy into ay. Then the current through the filament can be given by here delta I is equal to del q by del t. Previously we have considered the equation for I as q by t, charge per unit time. Similarly, for if you consider it for a small change, then delta I is equal to del q by del t. Right? So that is the equation which we have got. Delta I is equal to del q by del t equal to. Now we are representing, we have considered planar surfaces. Hence its density is given by rho s. Then charge can be denoted with q equal to integral s rho s into ds. Now for differentiation means dq equal to rho s into ds. So if you are again differentiating both sides, here differentiation integrating gets cancelled. dq equal to rho s into ds is the left one. Now from that dq, or in place of dq if we consider del q, then it is denoted with del q equal to rho s into delta s. Hence this del q is replaced with rho s into delta s. Now rho s into delta s by delta t. So here, and along with this, if you consider it for volume, then q equal to integral v rho v dt. Right? So if you consider a volume charge density, we have to consider it for in the three directions. Now that can be written as here for the three directions, the del q means from this dq, you write that equation dq equal to rho v into dv. Now here we consider rho v into this volume is denoted with divided with two surface area and line means then it is denoted with ds into dl, right? So three direction elements are divided into two directions and one direction element. So if you consider it for two directions, then the area becomes delta s and rho will be the constant. Rho v into delta s into delta l means one particular direction and we are considering it with velocity and the velocity direction is given by here y, hence that length will be given by here delta y by delta t. So delta y by delta t. And we know that the velocity u can be denoted with change in the direction is given by here y direction element, hence del y by del t, which is equal to rho v into delta s into, so this can be denoted with velocity and which is directed in y direction element as uy. Hence, delta I is equal to rho v into delta s into uy. Now, consider this as equation number 4. Now, to define that current density, here the current density at a given point is the current through a unit normal area at that point. So, J can be denoted with current per unit area, I by S. Now, according to that, we are going to derive the equation for convection current density as, so the bidirected current density and it is denoted with Jy is given by Jy equal to delta I by delta S. Now previously we have derived the equation for the this thing as delta I is equal to rho v into delta S into Uy. Now delta I is equal to rho v into delta S into Uy. Now here, according to the current density, Jy is equal to delta I by delta S. Now if we substitute in place of this delta I by this equation here, then rho v into delta S into Uy by delta S. So this delta S and this delta S gets cancelled. Now Jy is equal to rho v into Uy. So y-directed current density means the equation is to be considered is here Jy is equal to rho v into Uy. Or from this, in general, this convection current density can be given by J equal to rho v into U, right? Where J is said to be convection current density, current per unit area. Current is generally measured in amperes per unit area, hence it is the unit for that convection current density is given by ampere per meter square. Now, and the convection current is denoted with I and unit for that is given by amperes, right? So, in general, the convection current density J can be given by J equal to rho v into U. So, if the velocity is directed towards Y, hence J by direction component is given by rho v into Uy, then from that J equal to rho v into U. This is the equation which is called as convection current density and it is derived from the volume charge density and velocity of an electron, where U be the velocity of an electron. Okay. Then second current is called here conduction current. As the name itself tells us that conduction current requires conducting medium to conduct or to exhibit current. So when an electric field E is applied, the force on an electron with the charge is, generally we are representing charge of an electron with the negative and it is given by here minus E. So there are three different notations for charge. Sometimes we used to consider it as Q or sometimes we used to consider it as E or sometimes Q. But three are representing with the charge of an electron, right? So whatever may be the symbol we have considered over there, the meaning for that is representing charge of an electron. Hence, when an electric field E is applied, the force on an electron with charge minus E is given by F equal to minus E into E. and this can be obtained as F equal to QE or E equal to F by Q. And this is the equation which we have already learned is where E is said to be electric field intensity and it is given by force per unit charge. When that particular element is placed in electric field called then E equal to force by charge. Then from this F is equal to E into Q. Now here this force equation is given by minus E into E. Generally, that electron charge is represented with negative, hence F equal to minus E into E. So take this as equation number 1. Now consider that yes, equation number 1. Now in order to derive conduction current density, again we have considered another assumption as here. If an electron with mass m is moving with an electric field E, then average drift velocity U, then according to the Newton's law. So according to Newton's, basically the Newton's proposed 3 laws, then one of the law is used here. So if an electron with mass m and it is moving with applied electric field E with an average drift velocity U, then according to Newton's law, a statement is given by the average change in momentum of the free electron must match with the applied force. Right? According to Newton's statement, the law is given by here the average change in momentum of the free electron must match with the applied force. So here average momentum of the electron free charge that is given by mu by tau, where m is the mass of an electron, u be the velocity of an electron, and tau the collision between the electrons. So mu by tau was equal to minus E into E. So previously we have considered the force equation from electric field intensity as minus E into E. Now according to Newton's law, that is given by F is equal to mu by tau. Now these are the equations or two are expressed for the force. Now LHS part of these two are same, hence RHS part of these two are also same. Now according to this, minus E into E equal to mu by tau. Now from this, derive the equation for U. So U equal to minus E tau by m into E. Minus E into tau by m into E. So from this above equation, we can say that the velocity of an electron is inversely proportional to the mass of an electron and it is directly proportional to the applied field. Right? So from these two relations, we can say that velocity U equal to minus E tau by m into E. So now, according to that, here already we know that according to convection current density, J equal to rho V into U. And previously we have got the analysis here, U equal to minus E tau by m into E from the Newton's law and electric field intensity force equation. We have got the equation for U is given by minus E tau by m into E. Now here, if there are n electrons per unit volume, if there are n number of electrons which are exist in the unit volume, then the electric charge density is given by. So charge density in a given volume, hence we have considered its respective density as volume charge density rho v, and it is equal to minus n into E, where E is the charge of an electron and n represents the number of electrons per unit volume. So consider this as equation number 3. Now according to this, already we know that the convection current density which we have learned just now, that is J equal to rho v into U. Now substitute in place of this rho v by minus n into E and U by this equation. So rho v equal to minus n into E and U equal to this equation. Now if we substitute U and rho v in this convection current density, then J equal to minus n into E, then minus E tau by m into E. Right? So if you multiply these two, minus into minus becomes plus, then n E into E is E square tau by m into E. So this complete term which are expressed inside the brackets is replaced with sigma into E, then J is equal to sigma into E is called as the conduction current density. where sigma is said to be conductivity of the conductor and it is given by n e square tau by m. And generally, this conduction current density, which is given by J equal to sigma into E, and it is also called as point form of Ohm's law. So, point form of Ohm's law or conduction current density is given by here J equal to sigma into E. How it is said to be J equal to sigma into E is point form of Ohm's law. Means how it is analogous to Ohm's law. Means J equal to sigma into E is the point form of Ohm's law. And according to Ohm's law, V equal to IR. So how these two are analogous to each other means here V is given by potential difference between two or voltage and I be the current which is flowing through that conductor and R be the resistance which is exhibited. So here V, I, R are analogous to here means V is the voltage which is applied field as denoted with E and I is the current which is related to current density and R and sigma both are reciprocal to each other. So resistance is here and here conductivity. So this is the way we can consider J equal to sigma into E is called as conduction current density and it is also said to be point form of Ohm's law. This we need to remember, important one, right? So point form of Ohm's law or conduction current density. In order to derive that equation for this conduction current density, it requires medium. So such medium is called as here conduction medium or conducting medium. Okay. So we have learned here two current densities as one is JC, nothing but rho V into U, convection current density, and another JC called conduction current density and it is given by J equal to sigma into E. So rho is V is given by volume charge density and U be the velocity of an electron. And here sigma is the conductivity of the medium and E be the applied electric field. Right? So two currents we have discussed, conduction current and convection current. Based upon that we have derived the two equations for densities respectively, convection current density and conduction current density. Now based upon these two currents we are going to learn the next topic is your continuity equation. So in order to derive the equation for this continuity equation we have to consider one of the principle called charge conservation. So what actually this charge conservation, based upon this how the continuity equation is to be derived means according to the principle of charge conservation means the time rate of decrease of charge within a given volume must be equal to the net outward current flow through the surface of the volume. So what do you mean by charge conservation? Means the time rate of decrease of a charge within a given volume must be equal to the net outward current flow through the surface of the volume. Means the outward current flow is denoted with I. So generally the notation for current as I, outward current, hence the notation is given by I out. So current I out coming out of the closed surface is given by I out of equal to closed surface, hence closed surface S into density is given by current density as J into ds. Generally we know that J equal to current per unit area, then from this I is equal to J into S. Current density is multiplied with surface area, hence from this I out is equal to closed surface integral S J dot ds. Now by default we know that the current definition according to fundamental one, charge per unit time, that is dq by dt. dq by dt. So dq in, why we have considered here in means according to the principle of charge conservation, just now we have seen the time rate of decrease of, then I equal to minus dq in by dt. Decrease is denoted with negative, time rate of, that is d by dt. So time rate of decrease of charge within a given volume, hence q in we have considered charge q in, then I equal to minus dq in by dt. So here is the equation for I equal to minus dqn by dt. And similarly here, I out is equal to closed surface integral S j dot ds. So outward current flow, which is flows through the planar surface, and time rate of decrease of charge within a given volume must be equal according to the charge conservation. Hence, I out equal to I. Now, based upon these two relations, we are going to write the equation as I out equal to minus dq in by dt equal to closed surface integral S j dot ds. So collectively we can write the equation as I out is equal to closed surface integral S j dot ds is equal to minus dq in by dt, and consider that as equation number 1. Now, where Qn is the total charge enclosed by the closed surface. So, Qn is said to be total charge which is enclosed by the closed surface, and J is said to be conduction current density. Okay. So, now to derive this continuity equation here by the divergence theorem. As we know that divergence theorem gives the relationship between surface to volume integrals, and in general it can be given by closed surface integral S A dot ds is equal to integral V del cross A dot dV. So generally the divergence theorem gives us the relationship between surface to volume integrals. So this is the general equation. We are applying this general equation to the charge principles here. In place of A, here we have the vector as J, and it is denoted with closed surface integral S A dot ds. So in place of A, here we have considered J. So closed surface integral S j dot ds minus integral V del dot j dv. Okay, so consider this as equation number 2. Now closed surface integral S j dot ds is equal to integral V del dot j dv. But according to the principle here, minus dqn by dt can be written as d by dt, as we know that charge principles according to the three continuous charge, that is q equal to integral L rho L dl, integral S rho S ds, and for volume integral V rho V dv. Now consider these two relations. Now minus dqn by dt equal to, now substitute in place of q in by minus d by dt integral V rho V dv. So minus integral V, consider this as d by dt, and outside it can be represented with d by dt. If you take into inside the integration, then it becomes partial derivative term, hence minus integral V dou rho V by dou t into dv. So take it as equation number 3. Now substitute equation 2 and 3 in equation 1. So according to this equation number 2, closed surface integral S j dot ds is equal to integral V del dot j dv, and according to this minus dqn by dt equal to minus integral V dou rho V by dou t into dv. So these two equations in equation number 1 means that equation number 1 is given by previously. What is that? I out equal to minus dqn by dt equal to closed surface integral S j dot ds. Now if you substitute all these assumptions in that 2 and 3 in number 1, then here. So integral V del dot j dv. So previously what we have, I out equal to minus dq in by dt equal to integral S j dot ds. So from this equation number 2 here, integral V del dot j dv, and which is equal to minus dq in by dt is nothing but here minus integral V dou rho V by dou t into dv. Now if you observe here, both sides which are considering here integration with respect to the volume integrals. Hence this volume integrals gets cancelled on both sides. Then from that we are going to write the equation as del dot j equal to minus dou rho V by dou t. Right? So del dot j, j is given by here current density, conduction current density, and del dot j is equal to minus dou rho V by dou t, and consider that as equation number 4. Okay. So del dot j is equal to minus dou rho V by dou t is said to be continuity of current equation or simply continuity equation. Okay, so from the principle of charge conservation, according to that, the statement is given by previously. The time rate of decrease of charge within a given volume must be equal to the net outward current flow through that surface of the volume. According to that, you can say that statement is I out is equal to my closure surface integral S J dot ds equal to minus dq by dt. Now from that, we have got the final equation for the continuity equation as the del dot j is equal to minus dou rho v by dou t, or it is simply called as continuity of current equation or continuity equation. Why it is said to be continuity of current equation? Means all the terms which are derived with respect to the currents. Hence, continuity of current equation, or simply it as continuity equation, that is del dot j is equal to minus dou rho v by dou t. Now, the next term which we are going to learn is here relaxation time. So, in order to derive the equation for this relaxation time, we have to consider first the first Maxwell's equation to be derived for the electrostatic fields, and that too point form or differential form we have to consider. So, the Maxwell's first equation is given by here rho v equal to del dot d, which is derived from the Gauss law. So rho v equal to del dot d is said to be point form or differential form of the first Maxwell's equation. Now rho v equal to del dot d bar. Now by default j equal to sigma into E. So this is called as j equal to sigma into E as conduction current density. That is just now we have learned that j bar equal to sigma into E bar. Now and we know that the relation between D and E, electric flux density and electric field intensity, as D equal to epsilon into E. Then rho v equal to del dot epsilon into E. Now substitute in place of D by E. First consider this equation. Then in that you just substitute D by epsilon into E. Then rho v equal to del dot epsilon into E. Now if you take this epsilon as outside, then rho v by epsilon equal to del dot E bar. Now from the Gauss law which we have got, rho v by epsilon equal to del dot E bar. Now, so consider this equation rho v by epsilon equal to del dot E bar. Now from this equation, if you multiply both sides with sigma, then rho v by epsilon into sigma equal to del dot sigma into E bar. So what is this? According to conduction current density, J equal to sigma into E. Hence, if we substitute sigma into E by J here, rho v by epsilon into sigma, which is equal to del dot J. What is this del dot J? Just now we have learned. That is continuity of current equation, or simply current equation, that is given by del dot J is equal to minus dou rho v by dou t. Now, if we substitute in place of del dot j by minus dou rho v by dou t, which is equal to rho v by epsilon into sigma. Now, if we observe these two are the equations, so it consisting of some of the rho v components and the rest will be related to other. Hence, we can separate the rho v components and the rest, yes, like this. Then dou rho v by dou t equal to minus sigma rho v by epsilon. Now, from that, dou rho v by rho v equal to minus sigma by epsilon into dou t. So to get the equation for rho v, so consider both sides integration. Then integral v, then integral this term. So integration differentiation gets cancelled. Here resultant will be the rho v, and rho v naught is the integration constant into e power minus t by tr. So what actually this tr means? Epsilon by sigma. So where this tr is said to be relaxation time or a rearrangement time in electric fields. So rho v equal to rho v naught into e power minus t by tr, where tr is said to be epsilon by sigma, and it is simply known as relaxation time or a rearrangement time. So in order to derive this relaxation time or rearrangement time, we have to first consider the first Maxwell's equation from the Gauss law as point form rho v equal to del dot d, and according to conduction current density J equal to sigma into E, and the relation between D and E, D equal to epsilon into E. Now as the continuity of current equation del dot J equal to minus dou rho v by dou t. So like that, if you derive TR equal to epsilon by sigma, this is called as relaxation time or rearrangement time. So here integration of sigma by epsilon is a constant. We are integrating this one with respect to t, hence it becomes e power minus t by tr. So tr is said to be here relaxation time or rearrangement time. Okay, then Poisson's and Laplace's equations. So again, in order to derive Poisson's and Laplace's equations, we have to consider again first Maxwell's equation to be derived from the Gauss law, that is rho v equal to del dot d. Then rho v, relation between d and e is given by d equal to epsilon into e. Then rho v equal to del dot epsilon into e. So first consider rho v equal to del dot d. In that d by epsilon into e. Then rho v equal to epsilon into del dot e bar. Okay. Now why we have separated means epsilon is a constant and e is a vector. Hence rho v equal to epsilon into del dot e. Now we know that the relation between e and v. So that is e equal to minus del v. Now if we substitute in place of e by minus del v in this equation, epsilon del dot minus del v. So minus, then from that rho v by epsilon is equal to del dot del v minus del dot del v, or del square v equal to minus rho v by epsilon is called as Poisson's law. So del square v equal to minus rho v by epsilon, which is known as Poisson's law. Now in order to derive this Poisson's equation, first we have to consider here the first Maxwell's equation from the Gauss law, point form as rho v equal to del dot d, and the relation between d and e is d equal to epsilon into e. Then from the del square v we have got for the Poisson's law as del square v equal to minus rho v by epsilon. Now from this Poisson's law we are going to derive one more law called Laplace's equation or Laplace's law. So as a special case of the above equation occurs, previously how we have written for Poisson's del square v equal to minus rho v by epsilon. So consider this equation, and for a special case of this equation which occurs if rho v equal to 0. So if rho v equal to 0, then if we substitute here rho v equal to 0, then del square v equal to 0. So del square v equal to 0 is said to be Laplace's equation. So in order to write this either of the equations, whether Laplace's equation or Poisson's equation, then we have got equation as here previously. Poisson's and Laplace's equation. Suppose we want to express this Poisson's or else Laplace's equation as in Cartesian coordinate system, then del square v equal to 0. So del square v can be written as del dot del v. So del dot del v means del dot represents divergence of, del v represents the gradient of, and v stands for a scalar. Right? So firstly we are going to express this one in terms of v as dou v by dou x into ax plus dou v by dou y into ay plus dou v by dou z into az is the equation for del v, gradient of a scalar. Now we want to find the del dot term. Hence del dot del v can be written as dou by dou x into ax plus dou by dou y into ay plus dou by dou z into az into total this equation dot with this total equation. Now this can be collectively written as dou by dou x into dou v by dou x, ax dot ax value is 1. Similarly for the next case, dou by dou y into dou v by dou y, ay dot ay value is 1. Similarly, last case, dou by dou z into dou v by dou z, az dot az value is 1. So like that, if you multiply, the equation for that del square v can be written as dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square, which is equal to 0, is said to be Laplace's equation, which is expressed in Cartesian coordinate system. Okay, so in this lecture we have learnt there are 4 topics. First one is introduction to materials based upon the electrical property. Materials may be broadly classified into conductors, insulators, semiconductors, and conduction current density Jc is given by rho v into u. And the second one is conduction current density Jc is equal to sigma into E. So Jc both are representing currents only, current densities only. So here convection current density doesn't require any conduction medium, whereas in order to generate this, derive this conduction current density, it requires conducting medium. So it depends upon the applied electric field strength. Then Jc equal to sigma into E. Then third law we have learned is continuity of current equation, that is del dot J equal to minus dou rho V by dou T. And the next one is relaxation time we have got, that is Tr equal to epsilon by sigma. And next is Poisson's and Laplace's equations, that is del square V equal to minus rho V by epsilon as Poisson's. For a special case, if rho V equal to 0, then Poisson's equation becomes Laplace's equation, that is del square V equal to 0. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.